All right, let's tackle the first example in chapter 12. It is question 239. Now, by the way, this is an alternating current circuit. So let's read the question first. Question 239. In the accompanying figure, an alternating voltage power a mixed circuit. The voltage is given by V equal to 10 sine 314.6 multiplied by that time. Find, in part A, the frequency of the power source. Part B, the voltage between point A and B at time t is equal to 2.1 second. And part C, the average power dissipated by each resistor. Now, due to the nature of the problem, I'm going to be solving part C first, and it's mainly because I cannot fit everything on my board. And we need some information from part C in order to be able to solve part D, basically. All right, so we are given a circuit. It has six resistor, and it has a power source. So the power source we are shown on the diagram is written as 20 volt peak to peak. And basically volt peak to peak mean 10 volt peak. Volt peak to peak is simply twice the peak voltage. We have 6 resistors here. We got R1. Now, by the way, they are not denoted. There's no notation on the diagram. I decided that this one is R1. It is equal to 4 ohm. R2 is this one. It's equal to 12 ohm. R3 is equal to 4 ohm, R4 is equal to 4 ohm, R5 is equal to 4 ohm, and finally R6 is equal to 10 ohm. Just like we did in chapter 6, we can apply the mixed circuit rule to simplify this circuit. So the first branch we're going to simplify is this branch over here. We can combine R3, R4, and R5 to create one resistor. We simply add them up. 4 plus 4 plus 4 is equal to 12. So we now end up with this circuit. 20 volt peak to peak. We have 4 ohm over here. Now this is 12. It is in parallel with the other 12. Now, by the way, this is a simple trick, but when you have 2 resistors in parallel that share the exact same value, combining them is you simply have to divide by 2. So 12 divided by 2, we got 6. And if you're not convinced by that trick, by all means, use the complete formula. So we got 4, 6, 10 over here. I'm not going to do the other simplification. We can easily see that the equivalent resistance of the complete circuit is 20 ohm. So 20 ohm is the equivalent resistance. Let's write down all the resistance. We will also need them. So 4, 4, 4, 12, and 4. And basically, the voltage on the equivalent resistance is the voltage at the source. Now, what we're going to do is use the peak voltage, by the way, and I'm going to explain in a second. So the peak voltage at the source is 10 volt peak. Now, the problem when we write a ohms table like this in an alternating current circuit is the voltage is always fluctuating, all right? So since the voltage is always fluctuating, the current is also always fluctuating. So in order to solve this, we are going to calculate everything with respect to the peak voltage and the peak current. And then we will look at the ratio to answer our question, basically. All right, so, and by the way, it's equivalent to fixing the voltage in time at the peak voltage, at 10 volt. Okay, so it's completely equivalent. All right, let's go back to our equivalent circuit. So we got 10 volt peak, that we got 20 ohm, sorry, and that means we get 0.5 amp as our peak current through the power supply, basically, and our equivalent resistance. All right, so we got 0.5 amp going through the power source. That means there's 0.5 amp going through R1. This current is being split at the junction A. Some of it is going in that junction, some of it is going over here, and all of the current is going through R6. So we know the current of R1 and R6 has to equal the same current going through the power supply. So R1 and R6. And because we have the peak current, we can calculate the peak voltage. So the voltage at R1, the peak voltage is 2. The peak voltage at R6 is 5. All right, now one thing that will be useful is, I'm gonna erase the volt peak to peak here. Well, I'm gonna use 10 volt peak. So we know this is 10 volt peak. So the voltage at this junction is 10 volt peak. we lose 2 volt at after the first resistance. So that means there's 8 volt peak left at this point over here. We lose 5 volt here. This over here will be our 0. By the way, we are forced to choose 0 here because if this one is 10 and we just gain 10 volt over here, well, it has to be 10 minus 10, it has to be 0. Now, here, we got the current coming in that direction. So that means this side of the resistor is at a higher voltage than the side over here. That means there's a voltage drop when you're going that way. That means the voltage here has to be 5 volt. Okay, so now we got the voltage at this point. We got also the voltage at this point, and the difference is the difference in our in R2 basically. So the voltage drop in R2 is 3 volt peak. Sorry. So we can calculate the current going through R2. It is 0.25. Now note, we got 0.5 amp going in that direction, 0.25 going in that direction. That means that the current going into that direction is 0.5 minus 0.25, which is also 0.25. And note, it makes complete sense. When the charge arrive at this junction, they have the choice to go through that resistance or that one. Both of them share the same exact resistance, which means that they will split evenly the charge. All right, so now we got the current everywhere. We can easily calculate the peak voltage everywhere. Well, in this case, it's simply 1 volt, 1 volt, 1 volt. All right, now to find the average power, we need to find the voltage RMS. And no, by the way, I did not talk about these formula. So we got the voltage at a given time. So this is the voltage at the source, by the way. So the voltage over here is equal to the peak voltage multiplied by sine, 314.6 multiplied by the time. We will need to find the voltage RMS. So the voltage RMS is equal to the peak voltage divided by square root of 2. So that means for our first resistance, it's 1.4, well, 414 actually, just to be precise. For the other one, for the second one, it's 2.12. First one, 0.707. Just to make sure everyone can see these. So the voltage RMS at R1 is 1.414, at R2 is 2.12, at R3, 4, and 5 it's 0.707, and at R6 it's 3.53, and at basically at the power source it's 7.07. Now if we want to calculate the average power, we use that formula. Average power is equal to the voltage RMS square divided by the resistance. All right, so voltage RMS square divided by the resistance, this is 0.5. I'm not sure for the second one, let's have a look. So it's 0.375. Let's look at these. These are 0.125. This one is 1.25. And the power at the source is 2.5 watt. Now, by the way, if you add all the power dissipated through each resistor and you add them up, you equal the power supplied by the source. Obviously, energy is conserved. All right, now we are in this position. We will need to solve in part B the voltage difference between part A and B at a given time. So it will be very useful to figure out what is the voltage at point B. So we lose 1 volt peak on R3 and R4, which means here it's 7 volt peak, here it's 6 volt peak. And when you look, by the way, R5 is losing 1 volt, so 6 minus 5, yes, we are losing 1 volt, so everything worked just fine. If you need to pause the video and write down the Ohm's law table, do it now. I will erase that section to answer part A and B now. All right, part A, we're looking for the frequency. Now, that term over here in the formula for the voltage, so the alternating voltage, is our angular frequency. And basically, the frequency is equal to omega divided by 2 pi, in this case equal to 50 hertz. So that's really hertz, sorry. So the frequency is very easy to determine if you are given the angular frequency. All right, now one thing that's important is because the power, the voltage is coming from the power source, each of the voltage drop across each resistor will be a fraction of the power source. And basically, if we look at the difference between point A and B, it is 2 volt peak to 2 volt peak between these two. If we were to plug a multimeter here, we will measure 2 volt peak. There's 10 volt peak here, but they both share the voltage measure here and the voltage measure here. They both share the exact same frequency. So the voltage between A and B is equal to the voltage peak, and I'm gonna write VP AB sine of 314.6 multiplied by the time, and this has to equal to sine 314, and we're looking basically at time for part B. We're looking at time 2.1 seconds. So let's this is the answer to part B. We need to replace the time by 2.1. Once we input all the values, so 314.6 multiplied by 2.1, we get minus 1.72 volt. Now, by the way, if I were to ask a similar question in a test, I will use a much smaller time frame. If your calculator is not programmed in the same way as mine, this is a lot of cycle, and therefore you might get a very big difference in your answer, okay? So if you don't get exactly that answer, don't freak out. In a test, if I were to give a similar question, really the time frame will be something way shorter, so this value will be within one cycle, all right? That's it for question 239. As you have seen, there's not that many new concepts. All the technique used to solve that question is very similar to what we've been doing since chapter 6. All right, so in the next video, we are going to solve some problem related to transformer. And finally, in the last few video, we're going to be combining everything together. All right, see you in the next video.